Let's look at calorimetry. Calorimetry is an experimental way to determine the enthalpy. So if I took water at 25 degrees Celsius and I put it in a bucket and a cup, if I were to add 50,000 joules of heat, you would see that you'd have very hot water in the cup, but just warm water in the bucket. And that is because there is just a lot more matter in that bucket. Calorimetry is the science of measuring heat. You need to know the specific heat capacity or the specific heat constant, and it is the energy required to raise the temperature of 1 gram of the substance by 1 degree Celsius, or because 1 degree Celsius is equal to 1 Kelvin, it would be also 1 Kelvin too. The molar heat capacity, instead of just having 1 gram of it, we would have 1 mole of it. And this specific heat constant should be given to you. So, or you should be given enough data that you can solve for the specific heat constant. In these experimental problems, we use what's called a calorimeter. It basically is a styrofoam cup that has some water in it. My reaction takes place in the water, and I put the thermometer in the water so I know what's happening in the reaction. So the water will either absorb heat from the reaction, so the water temperature will go up, or the water temperature will go down because the water is supplying heat for the reaction. Here is the formula for calorimetry. So you'll often see it written like this: mc delta T. M is the mass, C is the specific heat constant or the specific heat capacity, and the delta T is the change in temperature, and it's always the final minus initial. Now over here we have a chart that lists all the specific heat constants, and I want you to see how high water is. If you compare water to these metals, you see that water has a very high specific heat, and that is because it can absorb a lot of heat before the temperature goes up. While metals, because their specific heat capacity or their specific heat constants are so low, it doesn't take much for metal to heat up. Because of this, we use water in our factories to cool reactions or in our combustion engines in our vehicles, and that is because water can really absorb a lot of heat before it ever boils. So in Unit 6, we talked about these cooling curves and these heating curves. So here we have ice as a solid, and it's heating up, its molecules are moving faster. And then we have the energy is going to breaking the bonds to melting it. And so we see that the molecules aren't moving fast because their temperature is staying the same. Instead, the energy is going to breaking that hydrogen bonding. And then we have a liquid, and we're heating our liquid, making the molecules go faster. And then we have our boiling point. The temperature stays the same because the energy is going to now completely breaking the hydrogen bonding between the liquid molecules. And then we have water vapor or water as a gas phase. When we're looking at calorimetry, we are looking at just this water part right here. And so because of this, the specific heat constant we're going to use is going to be right around 4.18, or sometimes it's 4.2. But generally they will give this to you unless you have to solve for it. Here is my formula. One thing that you should know with calorimetry, because we're not measuring the reaction, we're always measuring what's happening with the water or with the solution. We have to take what's going on in the water or the solution to figure out what's happening in the reaction. So in an exothermic reaction, I would get my water to go up in heat. It would feel warm. And so therefore, the reaction would be losing heat. So it would have a negative sign. And an endothermic would be opposite. So my water, the temperature would go down because that heat would be going into the reaction. And so your reaction would have a positive sign. So this is really important. One of these is always going to be negative. So if my reaction gives up heat, I would have a negative here and I'd have a positive here. Or the opposite, if my reaction absorbs heat, then my water, I would see the temperature go down. Let's do a sample problem. If I take 11.2 grams of sodium hydroxide and put it into 75 grams of water, and then we'll take the initial temperature and let's say it's 20 degrees Celsius. As sodium hydroxide dissolves in the water, it is going to give off heat. So this is an exothermic reaction. Let's say it stops at 50 degrees. So that would mean that my delta T would be 50 minus 20. It's always final minus initial. I would have 30 degrees for my delta T. And so we're going to find our heat that the solution absorbs. So let's write our formula first. So Q equals mc delta T. Now for my mass, I need to take the two masses that are there because we're making a solution. You need to add them up. So 11.2 and 75 grams equals 86.2 grams. So remember, it's for the solution, so we need to add those. So always plan on adding your solute and your solvent. And my specific heat is not given to me, so I'm just going to assume it's water. If it's not given to you in your packet, always assume it's water. But on the AP test, they'll tell you. And then my delta T, we already solved for it. It's a positive 30. So go ahead and doing my math, I get 10,809 joules. Now this is what's happening in the water or in the solution. If I were to analyze what's happening in the reaction, it would be the same quantity but just opposite in charge. So this is a negative 10,809 joules, and that's because this is the amount of heat that left the reaction. Well, this says calculate the energy per mole in kilojoules per mole. And so kilojoules per mole is my formula. So I need to find the joules, I need to find the moles, and divide it. And make sure you pay attention to the sign. So the solution is a positive joules, but in my reaction, it would be a negative joules. It does want kilojoules, so I'm going to divide this by 1,000. So I get a negative 10.81 kilojoules. And then my moles, because it's the reaction, not the solution anymore, I'm going to use that 11.2 grams. So when I'm doing the solution, I use them both together. But when I'm ever talking about the reaction, you're doing just the chemical. The molar mass is 40 grams in 1 mole. I get that from the periodic table. And when I divide this, I get 0.28 moles, which goes up here. And when I divide this out, I get a negative 38.6 kilojoules per mole. So they will always ask for a particular unit. Use that as your formula, and then just put what you know. Pay attention to the sign. If the solution is positive, that means that the reaction is going to be negative. And this is for an exothermic reaction. Endothermic is going to be all the opposite signs. So to sum up, when you're doing the mass of the solution, you need to add them together. So on the AP test, you're going to take your solute and you're going to add it to your solvent. So remember, in calorimetry, we are just doing this liquid portion right here. So we're just making the water molecules move faster. And so that water will either absorb or provide heat for the reaction. If you need an example of how to do heating curve problems where you take the amount of energy of your solid and your melting and your liquid and your boiling, and then you add them all up, make sure you see the video in Unit 6. All right, let's do some more calorimetry problems, which remember we're just in that water area of the heating curve. This is calculate the amount of heat in kilojoules required to raise the temperature of 25 grams of water from 20 to 80 degrees. So there's no reaction, it's just water. And so I'm just going to write my formula. My mass is just the water, so I'm going to use the 25 grams. And that specific heat constant of water, again, is given to us. And then our delta T, it's always final minus initial. So that would be 60 degrees. So I'd have 6,270, and this is joules. It asks kilojoules, so I just need to divide by 1,000. I'm going to have 6.27 kilojoules. And I make sure I have a unit on there, just in case I'm confused about whether it's joules or kilojoules. And that way the grader will know if it's joules or kilojoules. So this is the amount of heat that would have to be added to the water in order to raise that temperature. And so you can see that it is a positive number. Let's look at this next one. Suppose that 5 grams of aluminum and 5 grams of water are both at an initial temperature of 25 degrees. Each sample absorbs 100 joules of heat. Calculate the final temperature of each substance. So let's start off with our aluminum. Now because I have aluminum, I have to use the specific heat of aluminum. My delta T, remember, is final minus initial. And they're asking for the final temperature. So I'm going to set it up this way. And I have 100 joules here. My final temperature for the aluminum would be 47.2 degrees Celsius. Let's do the same thing, but for the water. And I get 29.8 degrees Celsius. So you can see that the aluminum, its temperature really went up high because it has a low specific heat, while waters with a higher specific heat, the temperature was less affected. A 100-gram sample of water at 90 degrees Celsius is added to a 500-gram sample of water at 10. Then it will reach a thermal equilibrium. What would the final temperature of dumping these two waters together? Well, thinking through this, I have a very hot 100-gram sample and a very, very cold 500-gram sample. And because there's so much water in that 10 degrees, I'm going to find that it's going to be lower. So it'll come up a little bit, but not above 50 for sure. So C is your answer. And it says calculate the final temperature of the water. So this one is set up a little bit differently. I'm going to have my water sample on one side and the second water sample on the second side. And I know that the hot water is going to lose heat, and I know that the cooler water is going to gain heat. And so you want to make sure that you put those signs in there just to show the flow of heat. Okay, from what we know, we can see that because the specific heat is the same, I can cancel that on each side. Make sure that this negative sign, you keep it. And it doesn't matter which one is negative, but I do know that one of them is going to lose heat, one of them is going to gain heat. So I want to make sure I have that there. And when you do your math and solve for the final temperature, you get your final temperature as 23 degrees Celsius. So a little bit different where you have to have that negative sign, otherwise your math doesn't work out. It won't make sense. Calculate the specific heat of platinum if I have this many joules of heat that is released when I have this many grams cooled. So I'm going to use my equation, and what I'm solving for is this C. So I want to isolate that. So I have my specific heat equals my Q divided by my mass times my delta T. Put in what we know. And when I do my math, I get a 0.134. And then notice all these units. So joules on top, grams on the bottom, times degrees Celsius. So those are our specific heat units.